is basically the flow of charge carriers. And if we talk about the charge carriers, then in an electrolyte solution charge carriers are positive and negative ions, and in a metal wire, the charge carriers are free electrons. Actually, in metals, atoms are fixed, so only free electrons can move. Applying a potential difference causes electrons to move with a drift speed, creating electric current. The unit of electric current is ampere, defined as 1 coulomb of charge passing through a cross-sectional area in 1 second. To measure current, we use an ammeter and it always connected in series. In this diagram, a battery is connected to a resistor, and the current passing through this resistor is 0.09 amperes. The device used to detect the current is called a galvanometer. It is very sensitive, which is why only a small current is sufficient for full-scale deflection. To enhance its range, a shunt resistance is connected in parallel. Usually, the value of this resistance is very small compared to the internal resistance of the galvanometer, so a large current passes through this resistor while only a small portion of the current passes through the galvanometer to avoid full-scale deflection. The range of the galvanometer is decided by the shunt resistance. A multi-range ammeter can be developed by using a selectable switch as shown in the circuit diagram.
The design formula for the shunt resistance is given by, where Rs is the shunt resistance, Ig is the full-scale deflection current of the galvanometer, Rg is the internal resistance of the galvanometer, and I is the total current to be measured.
Numerical problems will be solved in the last part of the video. The charge on charge is quantized. This is our next topic. To understand this topic, consider these two diagrams. The first shows discrete steps while the second one consists of an inclined plane. In the first diagram, if we consider the height of the step to be 10 cm, then you have the discrete steps multiples of 10 cm. You can step up at 20 cm, 30 cm, 40 cm and so on. You can't step up at 15 cm. But in the second diagram the height is continuous, you can reach up to any height. In the same way, charge also occurs in steps, not continuously. For example, the charge transferred between bodies is in multiples of the charge of one electron, which is approximately minus 1.6 x 10 raised power minus 19 coulombs. Now, let's solve a small question. How many electrons constitute 1 coulomb of charge? Using the formula Q is equal to Ne, where Q is 1 coulomb and E is the charge of 1 electron, we find the answer, approximately 6.25 x 10 raised power 18 electrons. Consider another relationship of electric current. Electric current equals to A N V Q, where A is the cross-sectional area, N is the number density of charge carriers, V is the average drift speed of free electrons and Q is the charge on an electron. This relationship is very important and extensively used numerical. Let's derive this expression. For this, consider a metallic conductor attached to a battery with length L and cross-sectional area A. Using the relationship I is equal Q by T, where Q is charge and T is time. To find the total charge inside the conductor, consider its volume and the number of electrons. Now multiply it by Q to get the total quantity of charge which is free to move. Now, what would be the time taken by the electron to travel through the cross-section? Use the formula for speed, and it would be L by V. Now, we have the expression for both, total amount of charge and total time taken. Substitute these values in the formula for current. Rearrange to get the formula. So this is the formula, which we want to derive. Now, let's discuss two commonly used terminologies, drift speed and current density. When talking about drift speed, consider the movement of free electrons in metals. In metals, free electrons move like gas molecules. However, unlike gas molecules, their movement is very fast and random. Some move left, some right, some upward. Despite this random motion, their net movement in a specific direction is zero. When a potential difference is applied, it causes the electrons to move in a specific direction. This average velocity with which electrons drift under the influence of an electric field is called drift speed. On the other hand, current density is defined as the ratio of electric current to the cross-sectional area through which the current flows. Now consider an exam question related to this topic. This paper is of May-June 2023, Paper 2, Question number 6, Part B. A cylindrical wire has length L and resistance R. The total number of free electrons contained in the volume of the wire is N. Each free electron has charge E. The potential difference between the ends of the wire is V. Determine expressions in terms of some or all of the symbols E, L, N, R and V for Part 1. The current in the wire. So we have to express the current in terms of E, L, N, R and V. Recall Ohm's law, current would be V by R. In the next part we have to find drift speed. To find the drift speed, consider the formula, which we have recently derived, I is equal to NAVQ. Rearrange it for drift speed. Now, substitute V by R in place of I and E in place of Q, and by definition of charge density, which is number of electrons per unit volume, substitute N equals to capital N over AL, where A and L combine to form volume. After substituting, rearrange to get the desired expression for the drift speed. In the next part, we have to find the average time taken for a free electron to move along the full length of the wire. For this, consider the formula of drift speed, which we have derived in the previous part. Substitute L by T in place of V, and now solve for T. So this is the solution of this question. And this is another question related to this topic. We will solve it in the last part of the video. And this is another question related to this topic. We will solve it in the last part of the video. The next topic is conventional current. The current that flows from positive terminal of battery to negative terminal of battery is termed conventional current. However, in the case of metals, the actual flow of current is due to electrons. Electrons carry a negative charge, so they move from the negative terminal of the battery towards the positive terminal, as opposite charges attract. This leads to a question: why do we define current in the opposite direction of electron flow? The answer lies in historical convention. When electricity was first discovered, the direction of current was defined based on the flow of positive charge from higher potential to lower potential. Just like water flows from a high level to a low level, or heat flows from a hot object to a colder one, it was assumed that electric current also flows from high potential to low potential. Later, when electrons were discovered, it became clear that they actually flow from the negative terminal, low potential, to the positive terminal, high potential, which is opposite to the assumed direction. But instead of redefining everything, scientists introduced the concept of conventional current, a flow that behaves as if positive charges were moving from positive to negative. This convention is still followed today because it simplifies analysis and calculations. Actually, the flow of positive charge has the same effect as the flow of electrons. To understand this better, imagine two boys riding bicycles down a road. One says, "The trees are moving behind us," while the other replies, "No, we are moving forward, the trees are stationary." Technically, the trees aren't moving, it's the boys. But from their perspective, it feels like the trees are moving. Similarly, even though electrons are the actual moving particles, we talk about current as if positive charges are moving in the opposite direction. So now, we have two terms, electronic current and conventional current. Throughout this course, we will use conventional current. So whenever we mention the direction of current, it is always taken from the positive terminal to the negative terminal.